All right. Let's talk about flux, directions. This is going to be mostly, the first part is going to be a mostly like physical science-y type lecture where we're going to use lots of words, almost no equations. Because the equations are the same. If you want to know that, just look at the Tuesday's lecture. But what's getting everybody confused are I'm going to do all 8 variants. You could have in this circle one, the B field going out and the B field going in. The dB/dt could go out, in, in. And so what I'm going to do is, it would be better if, put that there. So my B field and change in B field externally is going to be in red. So 1 and 2, the B field is out. 3 and 4, my B fields are in. The dB/dt out, in, out, in. And first thing that we typically ask is, in what direction is the flux? Now, the flux direction is parallel to the B. So if the external flux is out, or I'm sorry, the B field is out, then the flux itself is out. Now the whole idea of out and in being negative, out being positive. Can I what? Oh, zoom out. You want it. All right. Okay. And one of the things that we need to know is the idea of parallel, which means that the vectors go in the same direction. So for parallel, they both point up or both point down or both point left or both point right. There's the concept of anti-parallel, which means they go in opposite directions. One's left, one's right, one's up, one's down. In the case of the flux, its direction is directly parallel with B, and that's the external flux. Now, the the change, the d phi b dt is parallel to dB dt. So if the B field is changing upwards, so in this case, if I was to write B field values, it would be going +1, +2, +3. In this case, it would be going +3, +2, +1. In this case, it would be -3, -2, -1. And in this case, it would be -1, -2, -3. So those would be the B field values, like as an example, and how they would change with time. So the change in flux is always parallel to that guy. So in these two cases, the d phi b dt, in both of those cases, are out. And in both of these cases, they're in. And it is, what happens is, it's a natural phenomenon. We just see it. It is what it is. That if you have a change in flux, an electromotive force is created to counter that change in flux. Some of it is related to conservation of energy, stuff that we're not really going to go over in terms of working problems exactly with that. But the induced B, the induced magnetic flux, which I have here in green, anti-parallel with d phi b. Actually, let me write it in the right color. d phi b dt in red. So for the induced flux, the induced magnetic field, they're all in the same direction, but it's always opposite of that guy. Say that again?
Number 2, you just have d phi b. It's supposed to be over d.
Oh, d phi, yes. Now, my apologies to anyone who's colorblind. Occasionally I get one every semester. I think if you are colorblind, let me know and then I'll dial back, because occasionally the ones in green and red really are confusing to people with that trait. So when you're looking at this, flux is directly parallel or parallel with B. The change in flux with respect to time is parallel with the change in magnetic field. It is not, it could be parallel or anti-parallel to B, it doesn't really matter. But what it does matter is that those are parallel always. These are always anti-parallel with the change in flux with respect to time. Now that's the induced B field, or the induced flux. To get that flux to happen that way, this is where really the minus sign that we see in Faraday's law comes as a consequence of these having to be opposite. I just remember that they're opposite and then go with that rather than remembering that negative sign. I'm not very trusting of negative signs. But in order to get the induced B field in, and out, there has to be an induced current. To get the B field to go in, the induced I has to be counterclockwise. Or I'm sorry, clockwise. To get the B field to come out, the induced I has to be counterclockwise. And those are the 4 permutations. That's all it can be. If you get a problem like this, it has to be one of those 4. Typically what I do is for the versions, like if this showed up on the test next week,
Where are the numbers and how do you get them?
where does the numbers what?
Where are the numbers and how do you get them?
Well, how do you get the numbers is was covered in Tuesday's lecture in depth. So if you attended that lecture, if you've got the lecture and the notes, you can get the numbers from that. So I'm not, the question that you've asked requires a 45-minute answer. A 45 minutes that no one who actually went to Tuesday's class wants to cover again. So.
So the current direction is based off the induced.
Yes. So all of the, why are we now? So are we discussing questions about direction, or, I mean, if the class wants to talk numbers, we could talk numbers, but it's a very simple equation, and this seems to be what everybody has problems with the conceptualizing the directions. So what I'm covering here is I just want to straighten out, because I have people in my class or in my office, one after another, going, explain this. So I'm just doing it all right now. Yes?
How do we know the difference between the right-hand rule involving the B field on a circuit and finding the force of the magnetic field?
Well, in this particular case, there is no force on the wire that we're concerned about. So the only thing that we use the right-hand rule for here, and it's not technically the right-hand rule, I call it the wrap rule, is in order to get the B field to come out, you just have to sit there and go, and this was another question, I'll put this back up in a little bit if we need it. So if we have a loop where the current is going clockwise, and the question is the B field coming in or out? The thing that you do is, here, that wire, if we blew it up, is going to the left. Here it's going to the right. You put your thumb there, and then you wrap your fingers. So obviously the B field there is going in. So that technically isn't the right hand rule, but you use your right hand and you wrap it.
What do we use those directions for?
What directions?
The directions of the field, that's their back.
They help you decide, in the end, the bottom line is it helps you decide whether or not the current is going clockwise or counterclockwise. That's really the core answer that I'm looking for. Yes?
We might be about to cover this, but could you also show us on the circuit, when you give us the direction of the B field, the logical steps to get the current?
You mean when you're adding up the B fields?
Well, like in problem set 5, we have a changing area.
Yeah, I'm going to get to that.
Oh, okay.
That's the next. No, I'm going to show you this, and I'm not going to show you the other type of problem.
Yeah, just wanted to.
Yeah, that's going to come.
Okay.
I don't know.
So
Yeah.
do you write a rule based on induced cases to find that direction? Is that what we're making?
The correct question is you use the wrap rule to
Well, that's
determine.
what I meant. Yeah. But we're basing it on the induced, right?
Because it is in fact the induced current, which is creating the induced flux. All right. I see collectively the class's brain has exploded. Oh, put it up. Your homework up here? Okay. All right. You could wait to end the class, but okay. Whatever. I don't judge. I question. And grade. Oh. All right. Thank you for wasting the time. Any other questions on this before we move on to the other type of problem? Those are the 4, and typically for the bottom line of the test, what I do is there'll be 3 versions most likely, and then each test will get, like if I pick that as the 4 problem, each will get a different set. So.
Dr. Ashford,
Yes.
what is the unit for electromotive force?
Electromotive force units are in volts. And to kind of briefly hit that.
Is that the same as Tesla squared per second?
Yes, it could end up, yes.
The value of the induced change in flux, is that the same value as the original change in flux, but with an opposite sign?
Say that again.
The value of the induced change in flux, is that the same as the value for the original change in flux?
Yeah. They effectively balance.
Alright.
And so that's the gist. You could sit down and do the unit conversion for that, but basically it's that. All right, now. Five, 4. All right. All right, so the next example. You can have that page. Okay. So the way that the moving bar problem works is that the B field can only be going out or in. The bar itself can only move to the left or right. So there are 4 permutations in all of this, just like there are 4 permutations in the other type of problem. So anything with, and it's kind of the same thing, B field out, the flux is out. So in these 2 cases, the flux is out. In these 2, the flux is in. So here, this area, because the bar is heading to the right, that area increases. So for the bars heading to the right, the area goes up. Over here, because the bar is heading to the left, the area decreases. Now, in yesterday, kind of had an instructional epiphany in terms of explaining this. It's a lot like think of 213 equation of continuity and the flow. You could have, and so what are the 2 quantities of that flows based on? Area and velocity. The area for flow we can think of as the area of these circuits. The velocity is related to the B field. Bigger the B field, bigger velocity. B field in, water going in, B field out, water going out. And so when you think about this, in cases where the area is getting bigger, there's more magnetic flux able to get through. So in cases where the area is getting bigger, this flux is getting bigger. Here it's getting bigger out. Sort of like the wind is coming at you, the window's getting bigger, so you feel more wind. If the wind is going out and the window's getting bigger, more wind is getting out. So this the change in flux so if area increases, magnetic flux and change in magnetic flux are parallel. Here, the windows are getting smaller, so there's less wind coming through. They're decreasing, or you could say decelerating. So the magnetic flux will be opposite. So if,
Opposite because it's decreasing over time?
yes. So this is how I describe parallel. This is how I describe anti-parallel. Anti-parallel, they're parallel, but their vectors are in opposite direction. Now for the induced flux, the induced flux is opposite of this. So this one and that one, they're out. So the induced B field and flux has to be going in. The induced B field and flux is always opposite of this guy. So in this case, the induced flux change with respect to time is out. Oh, I'm sorry, it's d phi b dt is out, so the induced has to be in. For here, the induced go out. I really need to go back to go through the videos and find a lecture, because there was a lecture where, hard to believe, there used to be a day where my classes could fit in Lewis Hall 101, 95 students. And I sat there and on the whiteboard did all 4 permutations in these big 3x3 foot panels. And it's really good. But stuff like this is good enough. Now, in order to get the induced flux to go in or out, the induced current in this case, to get the B field in, has to be clockwise. To get the B field to come out, it has to be counterclockwise. And so those are the induced currents. And you could typically say that if you've got the B field coming out, you have to have a counterclockwise current. To get the B field to go in, you have to have a clockwise.
That's for both of the types.
Mm-hmm. Yeah. Yeah, this works for both. All right, now.
So to determine our induced current, are we looking at the induced B field or just the B?
The induced B field.
The induced B field.
Yes. I mean, it may be parallel or anti-parallel to B, depending on the situation.
Okay.
But the induced flux is what determines the direction of the current, and the current is the one that determines the induced flux.
Is there an induced change in flux over time?
What would happen, I mean, in situations like this, if the velocity of the bar is constant, then that change in flux is constant. There are, with enough time, back in the old days, semesters used to be like 15, 16 semesters, or 16 weeks. So I was able to cover a little bit more. There are things called inductors, which are coils. We're familiar with capacitors, but there's a thing called an inductor. It can store energy like a capacitor, but in the opposite way of behaving. And there just isn't enough time to talk about those things. With that, with inductors, their ability fades with time or increases with time, depending on the situation. In these ideal situations, the bar is constant forever. So, now the last part of these things, you have to use the force on the bar direction is I cross B. So in these two cases, I is down, but in this case, we're down, up, down, in, up, out, up, in. So anything where we have down and up, this external force is to the left. Here, current up, in, I'm sorry, not external force, magnetic force. That magnetic force is to the left. Here, up, out, to the right. Here, down the page, into the page, to the right. And what you will see is that in all four cases, the magnetic force and the velocity are always opposite. Through observation. Through observation, you look at it. In every single case, the force from the magnetic field on the bar is always opposite of the velocity. which means that the external force that's applied to this the external force is opposite of the magnetic force, and the external force is in the same direction as the velocity. Yes? For this one? Force of the bar is there. This is just an arrow pointing to it. And so those are the 8 variations, yes.
I understand that force of the bar is going to be opposite of velocity. Could you show me how you did it doing the rep?
Okay.
I just didn't.
Now, in this particular case, we're not using the wrap rule. We're actually using the right-hand rule for this. All right, let's just blow this guy up real quick. So the current is going from the bottom to the top of the page with regards to the bar. So that's up. B is out of the page, the external B. So the magnetic force is to the right. And that's it. That's all it is. Yes. Not the induced, it's the original. In fact, to make it so that's in red. So those are the 8 permutations. If you get this on the test, it'll be one of these 4. And then on the final, you'll get one of these 4. One thing that it's either on the problem set or on one of the tests. You need that the B field has a particular value at time t, and it's based on this equation. It's just a linear equation. So if we had, oh, I got a confused look in the middle of the room. I will explain. I could just hear your brain popping. Someone else had a question.
Can you put the other thing back on the first one? Okay, so how do you get so the induced I was that way, so how do you get the arrow for up on the bar?
For which one?
Like the one you had just looked at?
This one?
Yeah.
The current, induced current, is going from bottom to top. The B field is going out of the page.
Yeah, but why is your current induced current going, the arrow going down on the left side?
Well, because it's going clockwise or counterclockwise. If the current here was going up and the current there was going up, we'd just have a puddle of current. It moves in a circle.
It only matters about the current through the bar.
Yes. Question.
What's the difference between magnetic force and force of the bar and the external force?
The external force, it's technically the external force doesn't have to be there, but what happens is then the bar slows down and comes to a stop. This is to maintain you have to have that.
So, what's the difference in the magnetic force and the force on the bar?
F sub B is the force of the magnetic field on the bar.
Okay.
External force is the force that you are applying to the bar in order to keep its velocity constant. Yes.
Like last class, we had two formulas of force, the current times the length of the bar times the field, and then the field squared, space squared, the times the velocity of the bar. What was the difference?
One was the external, one is the force on the bar, the other one was the current. The BLV over R is the current. The B squared L squared B over R is the force. In a one of the few reasons why I like this dumb chalkboard situation. What happens is, if this was my loop, and this plate here is the demo, and really all this is just a big magnet, and that's a magnet too. So there's an intense magnetic field between these two plates. And if I took this and pushed it into the magnetic field, it's a lot like a moving bar. Because really what happens is this is just a big wire. And what you notice, I believe the Exploratorium has one in San Francisco. It's a common demo. And it looks like what a lot of them have. It's like a bow. It's like, you know how like saw, but instead of the saw blade, it's just this big loop of coil. And you take the coil and you put it into the magnet, and what do you feel? You feel the magnetic force pushing against you. So in order to maintain that push, you have to put an external force to keep the velocity constant. Likewise, you can think of the magnetic force as the friction. If you pull it out, the magnetic force is opposite again of the velocity, and you have to pull on it. Otherwise, it'll just come to a stop like this. So it's a really good demo to actually see it working. You always feel a force opposite of where you're pulling or pushing. If you push, it pushes back. If you pull, it pulls back.
Where's the FB for the fourth one? Where's the arrow for that?
Yes. Now, to address the explosion of the brain in the middle of the room. For these, each of these have certain properties. 1 Tesla, 2 Tesla, 3, -3, -2, -1, -1, -2, -3, 3, 2, 1. There's a change in B field. Some of the problems that I ask on the test, on the final, if this thing crops up, there was a sample problem. I think it's either in the test bank or in the test that I gave from last summer. All right, I'm gonna take this away. If at time is 0, the B field initially is +2. At time equals 4, the B field is -4 Tesla. What is dB dt? And for that, it's a lot like, I mean, you're just going to use a linear fit. B is B naught plus dB dt times time. Much like we say y equals y naught plus mx. That the slope of the line is the change in the B field with respect to time. So this is a plus, that's a t. They look a lot alike, I'm sorry. So I'm going to have to find this. So B minus B naught equals dB dt times time, or B minus B naught over t is dB dt. B is -4. B naught is 2. T is 4. So the answer is -1.5 Tesla per second. So for something like this, the B field initially is out, but the dB dt is in. So for that example. So that's a simple explanation of what was going on.
How do you know that the B field's out?
Because I said it was +2. And the reason, I don't think, once again, we're all familiar with X and Y. And then you go, well, is positive Z into the page or out of the page? Because Z is typically the third dimension. It is out of the page. Positive Z is out because there's a mathematical identity, X crossed with Y will give you Z. And that's because we live in an impressive right-handed coordinate system. X cross Y, Z. And so that's why I say that out of the page is positive. Yes? Because the dB dt was negative. If B is negative, it's in. If it's positive, it's out. It's the same thing with if dB dt is out, it's got to be positive. If dB dt is negative, it's got to be in. Well, I gave you that information. In some test problems, I actually ask for it. The one test problem that I had was, and we could do it. Yeah, we could do an example right now. you have a current. The I is 5 milliamps. The resistance of the loop is 20 ohms. I want to know if B naught is equal to 2 Tesla, when will it reach 1 Tesla, or when will it reach 3 Tesla? So it's either got to increase or decrease. So what is it going to happen? Well, I is V over R. This is a changing B field, not a changing area. That is the electromotive force. So I is area dB dt over resistance. So Ri over A is equal to dB dt. Now this is just going to give you the magnitude. Oh, I need an area. Let's see what numbers I need to make this work out right, or better. 20 times 0.005. That would give me 0.1. So I would need an area of 0.5 square meters. And that gives me a dB dt magnitude of 0.2 Tesla per second. Now that just gives me the magnitude. When you're looking at this, it's a counterclockwise current, which means that the induced flux has to be out of the page. So you've got a counterclockwise current in that loop, that induced flux has to be out. So if it's coming out, that means the external change in flux with respect to time is going in. The only way that you can get it if the area is constant is if the dB dt is also going in. So if the external change in flux is in for this particular setup, the change in the B field also has to be in, which means that because of this, the real value of dB dt is negative 0.2 Tesla per second. So it will not reach 3 Tesla. It may have been 3 Tesla earlier in time, but when will it reach 1 Tesla? So now T is equal to, or actually, B is equal to B naught plus dB dt times time, B minus B naught dB dt, T B minus B naught dB dt equals time. So my final B must be 1. My initial B is 2. My dB dt is negative 0.2. So my time must be 5 seconds. And an explanation of this type of problem, when if you look back at all the tests that I've ever given, for the first couple of years, this part at the bottom didn't show up. And I always felt that this type of, the circle, I was a big fan of the bar problems. Because the bar problems, you got to figure out the current, and then you got to figure out the magnetic force on the bar to maintain velocity and stuff like that. And I was like, well, I need to beef this thing up a bit, because I don't consider it a valid test problem. It's a good appetizer, but it's not a test problem. And then I figured out, if I've got a changing B field, I can start asking questions about, well, what's the rate and change of the B field? What is its initial B field? What is its final B field? At what time does this happen? And then that made it a legitimate problem. So a problem like this, if it showed up on the test, I could either give you the conditions. At time t, it was 2 Tesla. At time 5 seconds later, it was 4 Tesla. Give me the direction of the current and stuff like that. And then you would just start manipulating this. And
You know that it will reach 1 Tesla or that it's decreasing?
Because I know for a fact, and this is how I see it. I gave you the current as counterclockwise. Fact. That means the induced flux has to be out. A counterclockwise current produces a flux that's out. Lenz's law states that the induced flux must be opposite of the change in flux with respect to time, that external change. So if the induced flux is out, the external change must be in. If the external change in change in external flux is in, since the area doesn't change, the change in B field must be in. And if the change in B field is in, then the change in B field is negative. That dB dt is a negative value. So if we determined here that it's 0.2 Tesla per second, logic dictates that the true value of the magnetic field change is negative 0.2. And then there you go. And then that's it. So there's a lot of, the thing, in the past, if you talk to 214 students from like 3 years ago, they tend to say that the hardest test that Eschenberg gives is test 2 of 214. Because what are you dealing? Oh, nod your head. That just makes me stronger. Yes. Give me your evil. But so you've got Kirchhoff's law. You've got really the 3 that it's coming down to: Kirchhoff's law, magnetic induction, probably B field addition. B field addition will cover a lot on Friday's tutorial. I'll double check the times. It should be 2:30 to 4, and then we can go over that again some more on Tuesday. I'll double check to see, and for those of you who are packing up, you're correct. We're going to end this in about 30 seconds. We've got Tuesday as a review. I think we're going to have a review session. I'll try to see if we've got the time and place set up, and then we'll go from there. Have fun.
Hold on.